A very good evening to one and all present here. In today's class, we are going to discuss about the supersonic and hypersonic flow features in the rockets and missiles. Already we have discussed staging of rocket, what is the need for staging, those kind of things we have discussed in the previous classes. So here we are going to discuss mainly on aerodynamics and propulsion. Here we can have a small introduction about the supersonic and hypersonic flows. Supersonic and hypersonic flows are high-speed aerodynamic regimes encountered when an aircraft or missile travels faster than the speed of the sound. A flow is called supersonic when the Mach number is 1. That is supersonic means it should be greater than 1. That means between 1 and 5. Let's take. While hypersonic flow occurs when the Mach number is greater than 5. At these high speeds, the airflow behaves very differently from subsonic flow because the effects of compressibility become highly significant because the pressure, temperature, and density change rapidly around the vehicle, leading to the formation of shock waves and intense aerodynamic heating. These flow characteristics influence the design of aircraft, missiles, launch vehicles, and space re-entry vehicles. Understanding these features is essential for designing high-speed aerospace vehicles that are efficient, stable, and capable of withstanding the extreme thermal and aerodynamic loads. One of the most important characteristics of supersonic flow is the formation of shock waves. A shock wave is a very thin region in the flow where the properties of air such as pressure, temperature, density and velocity change almost instantaneously. When an aircraft or missile travels faster than the speed of the sound, pressure disturbances cannot move ahead of the vehicle. As a result, these disturbances accumulate and form a shock wave. Across the shock wave, the pressure rises suddenly, the velocity of the airflow decreases sharply, and the temperature increases because some of the kinetic energy is converted into thermal energy. Shock waves are also increase drag known as wave drag, which reduces the aerodynamic efficiency of the vehicle and it causes the energy losses. Therefore, the design of these things streamlined shapes such as pointed noses and swept wings to minimize the shock wave strength and reduce the drag in supersonic flight. Next, we can move on to the compressibility effects in subsonic, that means supersonic and hypersonic flows. The compressibility of air becomes a dominant factor, which affects aerodynamic performance. Unlike a low-speed flow, where air density remains nearly constant, high-speed airflow experiences significant changes in density due to the large pressure variations. The relationships between pressure and density becomes non-linear. It means that small changes in one property can produce large changes in the other. As the airflow passes around the vehicle, its pressure, density, temperature, and velocity vary rapidly from one location to the another location. These variations influence lift, drag, stability, and control characteristics of the vehicle. So, engineers must therefore use compressible flow equations rather than the incompressible flow assumptions while analyzing the designing of the supersonic aircraft or missiles and launch vehicles. Accurate prediction of compressibility effect is essential to ensure safe and efficient operation at high speeds. Next, we can move on to a very important topic called aerodynamic heating. Aerodynamic heating is one of the most critical challenges in hypersonic flight. When a vehicle travels at extremely high speeds, its kinetic energy is converted into thermal energy due to the compression and friction of the air surrounding the vehicle. This causes the temperature of the airflow to increase significantly, especially at the nose cone, wing leading edges, and other forward facing surfaces. In hypersonic flight, these temperatures can become extremely high and may exceed the melting point of conventional structural materials. Therefore, hypersonic vehicle require advanced thermal protection systems, that is called TPS. It is made up of heat resistant materials such as reinforced carbon composites, as well as ceramic tiles and ablative materials. These systems protect the vehicle from the excessive heating and maintain the structural integrity during high-speed atmospheric flight and spacecraft re-entry. Without effective thermal protection, the vehicle would suffer severe structural damage or complete failure. And finally, we can conclude the session on the features of supersonic and hypersonic flows. So in this session, we learned how shock waves are formed during high-speed flight, how compressibility significantly changes the airflow behavior, and why aerodynamic heating becomes a major concern at the hypersonic speeds. These aerodynamic phenomena play a vital role in the design and performance of modern missiles, launch vehicles, supersonic aircraft, hypersonic cruise missiles, and reusable space vehicles. So that's all about today's session. Thank you all.